can be used for remote sensing.
What's called
The wavelength, the electromagnetic radiation which has the smallest wavelength, which can be used for remote sensing. Ultraviolet, yes, ultraviolet. And what is the longest wavelength which can be used for remote sensing? Microwaves for remote sensing, and of course radio waves which can be used for communication. What is the difference between an active sensor and or difference between active remote sensing and passive remote sensing?
Active
Have its own
On source of electromagnetic radiation, and passive, it depends on an external source. Mostly it is the sun on which it depends. All of you seem very happy. Mashallah. Oh, what happened? Did you see something? Excited to see me. I am not that exciting. Anyways. And what is the relationship between the wavelength and frequency of electromagnetic radiation?
when some levels go high, another will go low.
So,
Let's
like,
call it
like if the wavelength is high, the frequency is high, the wavelength will be low. So, which is the electromagnetic radiation which has the highest frequency?
gamma.
Gamma rays, they have the highest frequency. Which is the electromagnetic radiation which has the longest wavelength? Radio wave, they have the longest wavelength. Which is the part of the electromagnetic radiation which we can see? Can we see all the parts of the electromagnetic radiation? No. The visible light, visible portion of the electromagnetic radiation we can see. Do you remember the wavelength of visible light? No, the wavelength, the length of the wave, the 400 micrometers to 700 micrometers. Sorry, not 400, 0.4 to 0.7 micrometers. It is like 400 nanometers to 700 nanometers. Between green and red part of the electromagnetic spectrum, which has a longer wavelength? Green and red. Red will have the longer wavelength. Which will have the higher frequency? Green will have the higher frequency. No, simple means if the wavelength is high, the frequency will be low. If the frequency is high, wavelength will be low. Can gamma rays and X-rays reach the Earth's surface?
No.
No. And why? What happens?
Become ozone.
Yes, means
Atmosphere.
in the atmosphere it is absorbed. You have molecules, gases like ozone, carbon dioxide, water vapor. These molecules, they absorb the electromagnetic radiations which have very small wavelength, or radiations which have high frequency, they are absorbed. So gamma rays and X-rays, they are absorbed in the Earth's atmosphere. Active remote sensing can be done at night, true or false?
What?
Active remote sensing can be done at night.
No.
yeah.
Active.
Active remote
Yeah,
sensing.
on-
Yeah,
So
on-
yes,
yeah.
you can do because it does not depend on the
Yeah.
sun.
Yeah.
It has its own source, so you can do it at night as well. We did all these. Okay, so we were about to start the interaction of the electromagnetic radiation with the atmosphere. Means we assume that this electromagnetic radiation is coming from the sun. Okay, as this electromagnetic radiation passes through the Earth's atmosphere, a few things can happen. And what are those things? Okay. Before radiation used for remote sensing reaches the Earth's surface, it has to travel through some distance of the Earth's atmosphere. Okay? Particles and gases in the atmosphere can affect the incoming light and radiation. In what sense? They can absorb, or they can reflect, or they can scatter the electromagnetic radiation. So these effects are caused by the mechanism of scattering and absorption. Basically, if you see here, three things can happen when the electromagnetic radiation passes through the Earth's atmosphere. Of course, the first one is the absorption. The electromagnetic radiation is passing or traveling through the Earth's atmosphere, and the particles present in the Earth's atmosphere, they absorb those electromagnetic radiation. So absorption means they are finished, they are no longer present in the atmosphere anymore, they are absorbed by the particles of the atmosphere. Second one is the scattering, means these electromagnetic radiation, they will strike with the particles present in the atmosphere, and they are reflected or deflected in different directions. Okay, so they are not absorbed, but they also cannot reach the surface of the earth. They remain in the atmosphere. They are scattered in the atmosphere. Scattered means they are sent in different directions in the earth's atmosphere. In the atmosphere they will be present, but they cannot pass through the earth's atmosphere to reach the surface of the earth. So second one is the scattering. And the third thing is the transmission. Some of these electromagnetic radiations which are not absorbed, which are not scattered by the Earth's atmosphere, they can pass through the Earth's atmosphere and reach the surface of the Earth. So what are the three things which are happening? Absorption, scattering and transmission. So which do you think will be useful for remote sensing? The absorbed radiation, or the scattered radiation, or the transmitted radiation? The one which is transmitted, transmitted, which can pass through the Earth's atmosphere and reach the Earth's surface. Only those electromagnetic radiations will be useful for remote sensing. So what are these means? The first one, scattering. Scattering occurs when particles or large gas molecules present in the atmosphere interact with and cause the electromagnetic radiation to be redirected from its original path. Means in absorption they are completely absorbed. You cannot see the electromagnetic radiations anymore. But in case of scattering, they are not absorbed but they are deflected in different directions. But they cannot reach the surface of the earth. Okay? How much scattering is taking place depends on a number of factors, including the wavelength of the electromagnetic radiation, the abundance of particle or gases, and the distance the radiation travels through the Earth's atmosphere. If the radiation travels for a smaller distance, the scattering will be less. If the radiation is traveling for a longer distance, the scattering will be more. And normally, the wavelengths, the electromagnetic radiation which have smaller wavelength, they are scattered more as compared to the electromagnetic radiations which have longer wavelength. Okay. So this is scattering, means you have the sunlight coming from the sun, it strikes the particles or the gas molecules, and also scattering will depend on the amount of these particles present in the atmosphere. If more particles are present, more gas molecules are present, scattering will be more. If less, then the scattering will be less. The second one is the absorption. Absorption is the other mechanism at work. In this case, the particles which are present in the atmosphere, they completely absorb the electromagnetic radiation and they do not allow them to pass. In contrast to scattering, the absorption phenomenon causes the molecules in the atmosphere to absorb energy at various wavelengths. And what are the main constituents or main particles which are present in the Earth's atmosphere which are responsible for absorption? The answer is it's ozone, carbon dioxide and water vapor. These are the three most important particles present in the Earth's atmosphere which are responsible for absorbing the radiation. Now this diagram, it shows you the difference between absorption, radiation, reflection and scattering. You see for example the first this thing which you see here, this is say for example the gas particle or the particle which we are talking about. Say this is a molecule of ozone. So as the sun rays or the radiation strikes, this one what is happening, it strikes and it is reflected back. Now reflection is not very common in the Earth's atmosphere. Instead of reflection, it is mostly the scattering. Means the original direction of travel was this one. After it passes through, comes in contact with the gas, the particles, it is redirected from its original path. It is no longer, yes, it's no longer in its original path, it is redirected, it changes its direction. So this is called as scattering. In the transmission, there is slight bend as it passes through the molecule, but then the overall direction of travel remains the same. It passes through the particles and it reaches the surface of the Earth. And this one is absorption, means the molecule, the radiation strikes the molecules and they are absorbed by the molecules. They no longer appear on the other side. So this is absorption. So when we are talking about the interaction of the electromagnetic radiation with the Earth's atmosphere, only the electromagnetic radiations which are transmitted through the Earth's atmosphere, only those radiations are helpful for, they are helpful for remote sensing. Okay. Now this brings us to an important concept which is called as atmospheric window. What is the function of a window basically? What does a window do? We have a window over here.
See light through it.
See light, we can see across what is on there. Means this is the wall, we cannot see across the wall. But the purpose of the window is that we have glass and we can see what is on the other side. Okay? So we have a window in the atmosphere also. Because of ozone, water, carbon dioxide and other molecules in the Earth's atmosphere, we are safe from harmful radiation. I told you, like X-rays and gamma rays, they are high energy electromagnetic radiations, and if it falls on the human body, it is very, very harmful. So there is a mechanism that all these high energy radiations, they are absorbed in the Earth's atmosphere itself. They do not reach the surface of the Earth. So that is why we are safe from these radiations. As a result, we only see specific portions of the electromagnetic spectrum. This phenomenon is known as the Earth's atmospheric window. Well, what is the atmospheric window? An atmospheric window is a specific region of the electromagnetic spectrum that can pass through the Earth's atmosphere with relatively little absorption. It's all the electromagnetic radiations which can pass through the Earth's atmosphere, they are a part of the atmospheric window. Those radiations which cannot pass through the Earth's atmosphere, they are not a part of the atmospheric window. So tell me, based on this definition, are infrared rays a part of the atmospheric window?
Yes.
Yes or no? He's saying yes. Can they pass through the Earth's atmosphere, infrared?
No.
It's reflected.
It's absorbed.
No. Infrared can pass through the Earth's atmosphere. Infrared radiations, they can. I told you when we are talking about the radiation, we said that the infrared radiations, they are used for remote sensing. So only those radiations which are reaching the surface of the Earth, only those radiations can be used for remote sensing of the Earth. So if infrared radiations can be used for remote sensing of the Earth, then that means they are a part of the atmospheric window. Are X-rays and gamma rays a part of the atmospheric window? Can they pass through the Earth's atmosphere? No, they are absorbed in the Earth's atmosphere. So X-rays and gamma rays, those radiations which cannot pass through the Earth's atmosphere, they are not a part of the atmospheric window. So gamma rays and X-rays, they are absorbed in the Earth's atmosphere. They cannot pass through the Earth's atmosphere. As a result, they are not a part of the atmospheric window. Portions of the ultraviolet rays, all portion of visible light, okay. Portions of the infrared radiations, parts of the microwaves, and almost the entire radio waves. These are the main components of the atmospheric window. If you look at X-ray or gamma rays and most of parts of the ultraviolet radiation, they are blocked by the Earth's atmosphere. They are absorbed in the Earth's atmosphere. They cannot reach the surface of the Earth. So, all parts of the visible radiation starting from 0.4 micrometers to 0.7 micrometers, starting from violet to red, all these radiation, the radiations which we can see with our eyes, they are completely transparent. That means they can pass through the Earth's atmosphere. They are a part of the atmospheric window. When you come to the infrared radiations, yes, most of the infrared radiations, you have small regions in between which cannot pass through the Earth's atmosphere, but most of the infrared radiations can pass through the Earth's atmosphere. Similarly, most of the microwaves, they can pass through the Earth's atmosphere. The radio waves, they can pass through the Earth's atmosphere. So all those radiations which can pass through the Earth's atmosphere, they are a part of the atmospheric window. Okay? So give me an example of two radiations which are not a part of the atmospheric window. X-rays and gamma rays, they are not a part of the atmospheric window.
Radio, it's a body.
Radio, yes, it's a part of that.
But
Yes. See, it is completely transparent. All the radio waves. Means if you look at infrared or microwave, you see these blue ones, this blue line. it is indicating absorption. Means the sum of the infrared radiation, sum of the ultraviolet radiation, sum of the microwave radiations, they are absorbed also in the Earth's atmosphere. Most of them can pass through. But radio waves, if you see, no radio waves are absorbed. They are completely transparent. All the radio waves, all the wavelength of radio waves, they can travel through the Earth's atmosphere. So the atmospheric window allows specific types of electromagnetic radiation to freely pass. Radio waves can pass through quite easily, but X-rays cannot and are blocked in the absorption band. But how does the atmospheric window relate to remote sensing? How is the atmospheric window related to remote sensing? So it says, scientists always keep the atmospheric window in mind when they design a sensor. They need to know which spectral bands sensors can measure. Okay? So this statement is important. Scientists keep in mind the atmospheric window when they design a sensor. So suppose there is a scientist, means you can design any sensor which can detect any type of electromagnetic radiation. For example, we go to the hospital, we use X-rays there. So that means there is a sensor which can detect that X-rays. That is why you are getting that sheet where you see the scan of, means the image of your bones. So that means the sensor is there which can detect that X-rays. Similarly for gamma rays also it can be done. But I am interested, or say a scientist was interested in remote sensing of the Earth, and he designed a sensor which can detect X-rays, and he attached that sensor to the satellite, and the satellite was sent in space. Now do you think that sensor can do remote sensing of the Earth? Should I repeat the question? A scientist, he designed a sensor, and that sensor could detect X-rays. X-rays coming from the atmosphere, that sensor could detect. And he put that sensor on the satellite, and satellite went in space. And what was the purpose of the satellite? To do the remote sensing of the Earth, not outer space, of the Earth. So do you think that sensor will be of any use? Why it will be of no use? Because the X-rays are not there. He will not be able to detect anything, because what is that sensor detecting? It is detecting the reflected energy from the surface of the Earth. He is doing the remote sensing of the Earth. So the electromagnetic radiation which is reflected from the Earth's surface, that is detected by the sensor. Now X-rays, they are absorbed in the Earth's atmosphere. They do not reach the surface of the Earth. So if they do not reach the surface of the Earth, there will be no reflection also. So what will be the use of that sensor? It will be a waste, no use, because he was interested in remote sensing of the Earth, and he designed the wrong sensor. He designed the sensor which was able to detect X-rays, and there are no X-rays which are being reflected from the surface of the Earth. So that means that sensor will be of no use for the remote sensing of the Earth. So that is why it is written, scientists always keep the atmospheric window in mind when they design a sensor. Okay, he will design a sensor for infrared radiation. Will it work? Yes, it will work, because infrared radiations reach the surface of the Earth and then they are reflected. Okay, so that sensor will work. If he designs a sensor for detecting the visible part, yes, it will work. If we design the sensor for microwaves, yes, it will work. For radio waves, it will work. But for gamma rays and X-rays, it will not work. And also, if you look at the atmospheric window which is shown here, even within the infrared and the microwaves, there are some portions, some wavelength of the electromagnetic radiation which are absorbed by the Earth's atmosphere. That means it cannot reach the surface of the Earth. So they have to know exactly which part of the electromagnetic radiations which wavelength of the electromagnetic radiations can reach the surface of the Earth, and keeping that in mind, they design the sensor. Suppose a particular range of the wavelength of electromagnetic radiation does not reach the surface of the earth. So if the scientist design a sensor for that particular wavelength of electromagnetic radiation, it will be a waste because that EMR is not reaching the surface of the earth, so there will be no reflection also, so they will not record anything. So therefore, they have to keep in mind the atmospheric window when they are designing a sensor. And what is an atmospheric window? Atmospheric window shows the parts of the electromagnetic radiations which can pass through the Earth's atmosphere. Okay, is it clear? Now, how atmospheric window is again related to remote sensing? Our eyes can see red, green and blue, which is a part of the visible light. These are the three basic colors or components of the visible light: red, green and blue, RGB. Okay. Now, suppose something is appearing in, we have this chair over here, this is appearing orange in color.
Yes.
Now, why it is appearing orange? Because all the other wavelengths of visible light, they are absorbed by this chair, and the orange one is strongly reflected. The others may be also reflected, but the orange one is strongly reflected. So that is why it is appearing green, orange. Okay.
You see
Or we can see orange. Or for example, this chair, it has dark red or maroon, whatever you want to say. Or this table appears yellowish in color. Why? Because the yellow one is reflected strongly, yellow part of the electromagnetic radiation, and the other part is not so strongly reflected. Something appears black, for example, this mouse is appearing black in color. So why it is appearing black? It is appearing black because all the absorptions are absorbed. If all the radiations are absorbed, it will appear black in color. If something is appearing white in color, then why it is appearing white? All the electromagnetic radiation, means visible part, they are all reflected in the same amount. That is why it is appearing white. Okay? If one is reflecting more and the other is reflecting less, then the one which is reflecting more, the object will appear of that color. Okay, the leaves, vegetation. What is the color of vegetation? Green. And why is it green? Because the green color is reflected more than the blue color or the red color or the other color. So it is appearing green in color. So this thing you have to keep in mind. This computer screen, the back of your computer screen, you see it's all black in color. Why it is black in color? Because it is absorbing all the radiations equally. So it is not reflecting any, so it is black in color. If something is white in color, because all the electromagnetic radiations are reflected in equal amount, the visible part, so it appears white in color. And if you see anything of any color, that means that particular part of the electromagnetic radiation is reflected more as compared to other parts. So that is why if you look at the color of the leaves or the vegetation, it will appear green in color, or anything which is appearing of a particular color. The reason for that is that that particular wavelength of the electromagnetic radiation is reflected more than the other ones. Okay? So healthy vegetation, for example, reflects more green light, and that is the reason why we see plants which appear green in color. Okay? Now, what are the sensors in our body with which we can see? Eyes are our sensor, and our eyes, they are designed only to see the visible part of the electromagnetic radiation. We do not see the radiations beyond the visible part. We cannot see ultraviolet, we cannot see infrared or microwaves or radio. Okay? But the scientists, they can design sensors to detect non-visible light as well. So as I told you, there can be a sensor to detect ultraviolet, there can be a sensor to detect infrared, there can be a sensor to detect microwave, and so on. Okay? So vegetation, okay, now when we look at a particular object, say here the example is given for leaf. The leaf appears green in color. Why? Because the green light is reflected more. But is that the only radiation which is reflected more, or is there any other radiation which is reflected more than green? Yes, there is a radiation which is reflected more than green, but that radiation is infrared radiation. Can we see infrared radiation? No, we cannot see infrared radiation, so it doesn't matter to us because our eyes cannot see. But if I design a sensor, if the scientists design a sensor which can see or detect infrared radiation, then in that case the leaves will, means the sensor will show that the leaves are much, means bright in infrared radiation. They will not appear green if you see, if they have a sensor which can detect the infrared radiation. And one thing I should tell you, that for seeing a color image of anything, we need three primary colors, red, green and blue. When you combine the three things together, then only you see the color image of an object. If you see an image in one color, in one band, that is either red or green or blue or infrared, what will the image look like? It will look gray color, black and white. There will be no color in that image. I can show you an example over here. This is in band 4, this is Landsat imagery in band 4. Band 4 for a Landsat imagery refers to red. Now this is only red, so if you see this image, what is the color of this image? It's black and white. Gray. It's in gray color, yes. So this is covering only the band 4 is for red color. So it is covering only the wavelength of the electromagnetic radiation which is for the red color. So I am seeing in one band, so that is why it is appearing as gray color. To see a colored image, what I have to do? I have to use three bands. Any three bands I can combine and it will appear, the image will appear in color. So you have one band for red, one for green and one for blue. When you combine the three, then it will appear in color image, it will appear as colored, but otherwise this will be a grayscale image. So if the scientist designs a sensor for one for red color, one for green color and one for blue color and one is for infrared color, okay, infrared region of the electromagnetic spectrum. So, and he is looking at the vegetation. Now when you are looking at black and white image or a grayscale image, if the reflection is strong, the part of the image will appear as white or black. If the reflection is strong reflection. So what will be the color, white or black?
White.
White, it will be white. I told you, if the reflection is strong, then in a black and white image, in a grayscale image, if the reflection is strong, then it will appear white in color. And if the reflection is zero, no reflection or very little reflection, it will appear dark in color. So the regions which you see here in dark, the reflection is low. The regions which appear in white or light color, the reflection is high. Okay. So I have the image of vegetation in red color, green color, blue color and the infrared radiation, in the infrared radiation. Now the leaves, they reflect a lot of infrared radiations, more than the green color. So if I have 4 different images of vegetation, one in red, one in green, one in blue and one in infrared. So where will the vegetation appear brightest or where it will appear white in color? Do you get my question?
No.
The leaves, they appear green in color. Now our eyes automatically, it combines red, green and blue. That is why we are able to see color image. Okay? If we were seeing only one band, one wavelength at one time, then we will see image like this, black and white. Okay? Now this image is from a sensor. Okay? this particular image is for red color. Okay. Similarly, you can have one image for green, one image for blue, one image for infrared. Now all the 4 images, they are separate. One by one, if you see 4 different images, they will appear same, black and white or gray color. Now, when and I am telling you that the vegetation or green leaves, okay, for the visible, when we see in the visible region, it appears green to us. Why? Because green is reflected more. Okay, so if I have the image of vegetation, 3 different image, one in red color, one in green color, and one in blue color. Now in grayscale, if the reflection is more, the thing will appear white. If the reflection is less, the thing will appear dark or black. So if I have the vegetation in red, green and blue, where it will appear bright? In red or green or blue? Light color, where it will appear? Which is reflecting most, red or green or blue?
On.
No, all is not reflecting. What is the color of leaf?
Violet.
Green. Now I am telling that I have separated, instead of using red, green and blue together, I separate red, one image for red, one for green, one for blue. So, but why was it appearing green to you? Because it was strongly reflecting green. So that means if I have a green image, green band image of the leaf will appear much brighter. It will appear white in color as compared to red and blue. Means you have 3 different images. One image in the red band, one image in the blue band, one image in the green band for the same leaf.
Yes.
So if you look at the color, and when you look at the leaf in one band or anything in one band, what will be the color? It will be grayscale. And in grayscale, if the absorption is more, it will appear black. If there is no absorption, it will appear white. It is reflecting all. So the leaves, you have red, green and blue. So where is the maximum reflection? In red or green or blue?
Green.
Green is the maximum reflection. So that means the green image will appear white. Green image will appear white. Means you are having 3 different images, one for red color, one for green color, one for blue color.
Green will be brighter.
Green will be brighter because green is reflecting more, so it will be brighter.
Red and blue will be green.
Red and blue will be darker than the green. Okay, means we are not combining the 3 images, we are looking at it separately. So the green one will appear brighter. So there will be no color in that, because I told you if you are looking in one band, it will appear black and white. So either you will see the color as black or dark gray or light white, off white or white. Okay. So in the green band, the leaf will appear very bright. Now I add one more band. I am adding infrared band also. I have a 4th image which is in the infrared. Now infrared we cannot see with our eyes, but sensors are there, artificial sensors which can detect that infrared. Leaves reflect maximum amount of light in the infrared radiation, but we cannot see that reflection because our eyes cannot see infrared. But if I have an image of the leaf in the infrared, now where will it appear brightest? In the red color, in the green color, in the blue color, or the infrared color? 4 different images of the leaves are there. One is in red, one is in green, one is in blue, one is in infrared. So where will you see the leaf like bright, more light will be reflected? In which band?
Green or infrared?
The 4th one, infrared will be more than the green. Infrared will be more than green. Infrared reflection for leaves is more than the green. But since we cannot see infrared, we see only the green one, so we say that the leaf is appearing green in color. But if you have a sensor which can detect the infrared radiation, the leaves will appear brighter in infrared. Okay? Okay, so scientists can design sensor to detect non-visible light as well. For example, vegetation reflects near infrared, which is invisible to human eye, but sensor can detect this electromagnetic radiation. And in fact, vegetation reflects more near infrared radiation as compared to the green part of the electromagnetic radiation. So if you have an image of vegetation in the near infrared, it will appear much brighter as compared to if you have an image in the red or green or blue region. Okay? So this means after the interaction of the Earth's electromagnetic radiation, we have the interaction of the electromagnetic radiation with the Earth's surface. So in the Earth's atmosphere, what is happening? Some electromagnetic radiations, they are scattered, some are absorbed, and some are transmitted. Now those electromagnetic radiations which are transmitted through the Earth's atmosphere, they will reach the surface of the Earth. Now once they reach the surface of the Earth, again three things will happen. Some radiations, they will be absorbed, they will be lost. Some radiations, for example, if they are falling on water bodies like lakes or rivers or ocean, they will pass through that water, and after some distance it will be lost. They will be transmitted, but ultimately they will also be lost. The other radiation, they will be reflected from the surface of the Earth. So for the remote sensing, only the reflected radiations will be helpful because you have the sensor in the Earth's atmosphere. Now the electromagnetic radiation from the sun, it is transmitted through the atmosphere, it reaches the surface of the Earth, it is reflected from the surface, and then it is recorded by the sensor. So when you are talking about the interaction from the sun to the Earth's surface, only the transmitted radiation will be helpful, and from the Earth to the sensor, only the reflected radiations will be helpful. Radiations which are absorbed, radiation which are scattered, they will not be helpful for remote sensing. Radiation that is not absorbed or scattered in the Earth's atmosphere, they can be transmitted through the Earth's atmosphere, they reach and interact with the surface of the Earth. So over time, okay, just this slide and then I will. There are three forms of interaction that can take place when energy strikes or is incident upon the surface. And what are the three forms? First one is the absorption, it is absorbed. Second one is transmission, especially if it is through the water body. And the third one is the reflection. So which part will be helpful? From the surface, the reflection. From the atmosphere, it is the transmission, and from the surface of the Earth, it is the reflection which will be useful. Okay, so we'll stop here.